A very good morning to my fellow friends and lecturers. My name is Kimberly Gore, and today I will be presenting my FYP project, which is the synthesis of nickel boride nanoparticles for energy conversion catalyst materials, the effect of annealing temperature. And my supervisor for this project is Dr. Noor Akmal. So first I will start from introduction. And from my research background, we can know that nanoparticles are particles within the diameter range of 1 to 100 nanometers, and one of the common usage of nanoparticles is in fuel cell catalyst. So one of the reasons why nanoparticles are commonly used in fuel cell catalyst is because the nanoparticles has a very small size and able to provide a high surface area to volume ratio. So the catalyst is also able to minimize more of the over potential and also lower more activation energy during the reaction when nanoparticles are used. So nickel-based nanoparticles has actually been proved to have similar catalytic effects compared to some other novel and commercialized catalyst material like palladium, platinum, rubidium, and iridium. So my problem statement from this project is to study the effect of annealing temperature on the change of crystallinity of nickel-boron nanoparticles, and to investigate the change in structure and catalyst performance of nickel boride nanoparticles through the addition of carbon support during synthesis process, and also to study the catalytic performance of annealed nickel boride nanoparticles on methanol oxidation. So the objective of this project is to investigate the effect of synthesis process parameter on the synthesized nickel boride nanoparticles, characterize the nickel boride nanoparticles using various characterization methods, and also to test the catalytic activity of the selected synthesized nanoparticles. So the scope will include synthesizing nickel boron nanoparticles through wet chemical synthesis from the chemical reduction of nickel chloride and also sodium borohydride. So the synthesis process parameter that will be varied will be the annealing temperature, and characterization method used will be XRD, XPS, SEM, and EDS. And cyclic voltammetry will be used to test the catalytic activity of the nanoparticles towards methanol oxidation. So now I'll be continuing on my literature review. So first I'll be talking about catalysis. So catalysis actually accelerate the chemical reaction to form a product. So usually there are two types of catalysts. The first one is the homogeneous catalyst, and the second one is the heterogeneous catalyst. So for homogeneous catalyst, usually the reactants are in the same phase, while for heterogeneous catalyst, the reactants are in different phases. So here we will be focusing on heterogeneous catalysts since most of the fuel cell catalysts are involved in heterogeneous catalysis. So the mechanism of heterogeneous catalyst includes the absorption of the reactants towards the catalyst surface and then undergoes surface reaction to form a product, and after that the product will dissolve or leave the catalyst surface. So for nanoparticle synthesis, there are actually two methods. The first one is the top-down method, where it involves the breaking down of bulk materials using high thermal pressure and mechanical pressure to form the nanoparticles. While the second method will be the bottom-up method, where the nanoparticles are built from its basic form, usually from its atom, through transformation or molecular condensation. While here we'll be focusing on wet chemical synthesis, where chemical solutions or chemical precursors are used to synthesize the nanoparticles at very controlled, proper experiment conditions. So for the advantages of top-down approach, it is able to induce chemical reaction which can improve the structure of nanoparticles and form agglomeration-free nanoparticles. While the disadvantages is that there might be a possibility of contamination of nanoparticles from its milling tools, and also the size and the shape cannot be controlled, and also the tolling cost is very high. So for bottom-up approach, the advantage includes that the nanoparticles' size, shape, and even porosity can be very finely tuned, and the nanoparticles can be produced in bulk quantities. Other than that, the nanoparticles produced are more uniform in shape and size. So the disadvantage for bottom-up approach is that the use of chemicals during the synthesis process might not be environmental friendly, and also the synthesis process might be very time consuming and very sensitive towards the parameters. So now we'll be talk about electrocatalysis, which is usually involved in fuel cell catalyst. So it is actually electrochemical reaction that involves heterogeneous catalysis and usually occurs at the electrode and electrolyte interface. So at the electrode and electrolyte interface, ions are usually attracted or absorbed towards the electrode surface, and usually positively and negatively charged ions will layer up at the electrode surface to form a double layer capacitance. So this is why catalyst is also very important in increasing the rate of reaction, is that when we use catalyst, there's more ions that can be absorbed towards the catalyst surface, which in turn increase the rate of reaction. So some of the energy conversion reaction in fuel cell includes water splitting, redox reaction of sodium borohydride, and also methanol. So now we'll be looking into direct methanol fuel cell. So some of the commonly used catalysts for anode and cathode for DMFC is platinum or platinum-based metal alloy. So some of the advantages is that it can provide a very good absorption surface for methanol, and it also has the most reactive catalyst. So the disadvantages is that platinum is actually very expensive, and also there's a tendency of poisoning of platinum towards methanol during the anodic and cathodic reactions. So now we will be looking into nickel-boron nanoparticles as electrocatalysts. So nickel-boron actually shows very good catalytic performance in various electrocatalytic reactions like HER, hydrogen evolution reaction, methanol oxidation, and also oxidation of sodium borohydride. So we can see here is a pre-annealed nickel-boron nanoparticles which form an amorphous structure. And from the XRD image here, the A here is actually the amorphous nickel-boron, which usually form a very broad peak at 45 degrees, while B is the annealed nickel-boron nanoparticles which form nickel boride, which form very sharp peaks of nickel phases due to its increase in crystallinity. So now we'll be looking at the effect of temperature towards the electrocatalytic performance on methanol oxidation for nickel boron. So we can see that from the SEM result here, amorphous nickel boron and nickel boride actually doesn't have any much differences. However, the current density actually increases from a 45 to a 65 ampere per gram after the nickel boron nanoparticles have been annealed. So this actually shows that the electrocatalytic performance of nickel boron towards methanol oxidation actually increases after nickel boron have been annealed. So now we'll be talking about catalyst support in nickel boron nanoparticles. So the role of catalyst support is to fix the catalyst onto the catalyst support surface in order to maximize the surface area of the catalyst. So some of the requirements for catalyst support includes high surface area, low combustive reactivity, high electrochemical stability, and also high conductivity. So these carbon support actually all fulfill these requirements, and also it is available in low cost and has mass availability. Also, it also has a presence of different porosity, which includes microporous, mesoporous, macroporous, or even trimodal porous. So here we can compare nickel boron nanoparticles without carbon support and nickel boron nanoparticles with carbon support. So we can see that from nickel boride, or different molar ratio of nickel and amorphous nickel and boron, we can see that the size actually ranges from 30 nanometer to 40 nanometer. However, if we add carbon support toward nickel-boron nanoparticles, we can clearly see that even though it has been annealed from 200 degree to a 500 degree Celsius, the size of the nanoparticles still remains very small, which is from 8.6 nanometers to 18.5 nanometers. So as a summary, nickel-boron actually has a very good catalytic activity in energy conversion reactions. However, the effect of annealing and addition of carbon support might actually increase the catalytic performance on these energy conversion reactions. So now I'll be continuing on my methodology. So first we will start from the synthesis of nanoparticles and then followed by XRD analysis to test the presence of nickel-boron nanoparticles and followed by annealing of nanoparticles. And then we'll undergo cyclic voltammetric testing to test the catalytic performance of nanoparticles and then undergo characterization through SEM, EDS, XRD, and XPS. So for the nanoparticle synthesis, we'll be using wet chemical synthesis through chemical reduction method. First, we will add the Vulcan into dispersed nickel chloride solution with ethylene glycol solution and add drop and undergo sonication. After that, drop wise of sodium borohydride will be added into the solution and then undergo centrifugation. After that, we will freeze dry the nanoparticles using a triple neck flask connected to a pressure gauge and immersed in a dry ice. So after that, we'll undergo heat treating where will be purged with argon gas. So for the characterization, we will undergo SEM and EDS testing where we will study the morphology and also the presence of the elements on the surface of nickel-boron nanoparticles. For XPS, we'll study the chemical state of the nickel boride nanoparticles, while for XRD, we'll actually know the crystallinity of the nickel boride nanoparticles after being annealed at different temperature, and also we can identify the size of the nanoparticles through Serre's equation after using the assumption of each particles actually consists of a single crystal. So for the catalytic testing, we'll be using cyclic voltammetry testing or the 3-electrode system where all three electrodes will be connected to a potential state, and the counter electrode will be the graphite electrode. The sample electrode will be glassy carbon electrode coated with nickel boride nanoparticles, and then the reference electrode will be the mercury oxide electrode. While for the electrode with electrolyte, it will contain sodium hydroxide and also methanol. While for the sample electrode, we will have to prepare by dispersing the catalyst or nickel boride nanoparticles onto naphthalene isopropanol hybrid solution and undergo sonication to form a homogeneous ink. And then the glassy carbon electrode will be polished by alumina series, and then the mixture will be loaded onto the glassy carbon electrode. So this will be my project Gantt chart for UGP1 and also UGP2, and these are the reference that I have used. That's all from me. Thank you.